This is Timothy Wood with the Citadel Civil Engineering Program. This is CIVL202 Statics, and in this video, we're going to be discussing equivalent systems. So just like in the last video, we discussed equivalent moments, where we said there were lots of different ways we could generate the same applied moment, the same external reactions. With equivalent systems, we're going to dial this all the way up. So the idea of an equivalent system is a system of applied loads. So we're not talking about reactions right now. We're talking about all the push and pull that might be acting on the body that we need to be able to synthesize or summarize and then resist. This could include both applied moments and or forces. Later we'll talk about distributed loads, totally here in the same context as well, that share common external reactions and resultants. The key word here is external reactions and resultants. When you get in mechanics of materials in the next semester, keep in mind that today is the best day to learn statics because you're going to be using it in the future. You're going to be looking at internal forces a lot, internal stresses, and our equivalent systems are not internally equivalent. They're only externally equivalent. So let's focus on this resultants piece today. With the resultants piece, we're saying, what's the resultant force? What's the resultant moment acting on the system? And in this case, we're going to have two things. So if we think about our resultant forces are simply the sum of all the applied forces. This is exactly what we had in our particle discussion. Our particle analysis. Okay? When we think about our resultant moments, it gets a little bit more complicated. Not really, but we remember that our definition of a moment from a force is going to be R cross F. And so we need to sum all of those up. But we might also need to add in those applied moments. So it might be that we're just grabbing hold of the system and twisting somewhere. We don't have the uniquely identified R cross Fs. Maybe there's two forces equal in magnitude, opposite direction, separated by a perpendicular distance that we're able to identify. When we add them up, they generate no net force, so they wouldn't contribute to our resultant force, but they would generate that moment. So we're going to have to also sum our applied moments, remembering that our position vector, so if this is about some particular point, all of our position vectors have to be back to that point, but our applied moments are all free vectors, right? They're all going to have the same value no matter where we model them. So they're going to have these systems are all going to have common resultant forces and resultant moments. So we have our applied moments and our force-generated moments. Now, it turns out that there are actually three classes of equivalent systems. Okay, three classes of equivalent systems. So we need to talk through what those are. This would be, the first one would be many forces and moments. So many loads, many of loads, forces, moments, distributed loads, all these sorts of things. And so if I were to draw a sketch of that, so this is at many locations, this would be something like this. So maybe I've got a beam that I'm designing, and it's got a ton of forces, loads being applied to it. So maybe there's some gravity loads, maybe there's some uplift pressures like earthquake loading, maybe there's some other beams that are causing moment to be applied at the end, all sorts of things like this. So this would be our kind of closest to our real model of what reality would look like. So we have these applied loads. Now, the other thing that we can do is we can come up with a resultant moment. So this would be our second class, a resultant moment and force at a particular location. So the idea is that if I take this and I sum up all my forces and I sum up all my moments, let's say that I pick some arbitrary point here, O, to sum my moments about, I could turn this into an equivalent system, something like this, which would have one force and one moment, our resultant force and our resultant moment, in fact, about this point O. Okay? So the idea here is that I'm simplifying the many complicated loadings into one force and one moment. This is the equivalent to having all of our dogs and turning it into the resultant force, an equivalent system of a single force being applied at a point. It's exactly what we're doing here. So we're bringing together that idea of equivalent systems from particles, resultant force, pulling on it. We're bringing in the idea of equivalent moments. Free vector can be applied anywhere, although this is about a particular point, right? About a particular point. And our resultant force. And so we're able to simplify this loading down to here. And this can be very helpful to us when we're doing design, that we're not actually worried, at least for calculating reactions, about all the complicated things. We can simplify it down to this level. So that would be the second class. Our third class is going to be a resultant force at a particular location. A resultant force alone at a location. So it might look something like this. I've got my same beam. I've got my reference point. And now what I want is, instead of applying a moment like this, I'm going to have some distance, x, to where my resultant force is applied. I could also have it move up and down, but the idea is that in this case, there's no moment applied to the system. So the question would be, okay, I've got a complicated loading, and I can calculate the resultant force and the resultant moment for that, and then I can just put that force at the point, and I can put my moment at the point and sum my moments about, and now I've got my equivalent systems. But how do I go from here to this picture? And the question comes back to, well, what is the moment generated by a force? So if we go to our FE reference handbook, we would find that the moment about the z-axis for a particular force is going to be equal to our x distance times the y component of the force minus our y distance times the x component of the force, like so. And so if I want to put a force somewhere on the x-axis, what I'm implicitly doing is I'm going to set my y value to 0. So this goes to 0. And then this whole term will go to 0, and then I can solve for that x distance. So over here, my x distance is going to be equal to our resultant moment divided by, the force in the y direction. And I'd be able to identify this clearly. The units will work out for us, because our moment's going to be Newton meters divided by newtons, or pound feet divided by pounds, so we'll be left with an appropriate unit for length. Such that when we go back and we calculate our resultant force for this system, well, it's the same resultant force. And then when I do my r cross f, so x times fr would give me that value there. And we'd want to follow through our signs. If I was interested in the y direction, so let's say that I had two equivalent systems that had a slanted moment. So let's say I've got two equivalent systems that had a slanted force. So let's see if I can generate something that makes sense. Here's a resultant force about some point. So this is our first, actually this version here. And we're going to have some resultant moment acting on it. You'll notice that I'm only drawing this as the scalar values here, because I only need the scalar values here because I've actually drawn the arrows next to them. Okay, so I've got something like that going on. Now, when I look at only the y component and the x distance, I can take my moment, divide by FR, Y. So I'm going to have a negative moment divided by a negative resultant force. And I would get a positive X value. And so I would have a force like so, FR at some distance, X from point A. That's an equivalent system of the third class. Alternatively, I could solve for the Y value. So let's say I set my X value equal to 0, and I could solve for the Y value. When I do that, my Y value will be equal to negative mr with respect to O divided by the X component. Okay, so in this case, that would give me a negative value. So if I were to draw another equivalent system, point A, I would have my force, FR would be down here now, and this would be my Y distance. Something like that. So that would be another equivalent system of the third class. Now, to really wrinkle your shirt a little bit, break your brain some, what we're doing when we solve this equation is we're actually finding the line of action the resultant force has to act upon to generate that same resultant moment. Okay, so this has been equivalent systems. Just to sum up, equivalent systems have the same common resultant forces, so resultant force, resultant moment. We can have a complicated loading like this. We can simplify it to a force and a moment at one location just by calculating the resultant force and resultant moment. Or we can divide through the moment divided by a component of the force to find where we could apply the force and need no moment. So this would be our simplest case. In some cases, the design is built on this, and we call this value an eccentricity. That's kind of some bonus content for you. We'll work an example problem like this during the class, and hopefully this gets us well on the way. Come with questions, and I look forward to talking to you then. Take care.